Okay, so let's just write some reminder information here to help us on this page. We know that our original function was x to the fourth minus 4x cubed plus 5. And we know that our derivative function, when we found that, was 4x cubed minus 12x squared. Why do we care about that? Because right now it wants us to find concave up, concave down, and inflection points. And we know to do that, we need to find the second derivative. So the second derivative of this function, using simple power rules, it's a polynomial, should be easy for you, would be 12x squared minus 24x. Again, we set that equal to 0 or undefined. This is never undefined. It's a polynomial function. I try factoring it. I realize I can pull out a 12x. What I'd have left over would be x minus 2. I set that equal to 0. When I set that equal to 0, I set each one of the factors equal to 0. 12x equals 0 gives me x equals 0. And x minus 2 equals 0 gives me x equals 2. Again, these are not critical values, but they are possible inflection points. And this is what the numbers that I'm going to plot on my number line, so I'll do so now. Again, I'm plugging them into the second derivative. Here's 0. There's 2. Let me consider the first interval would be negative infinity to 0. The second interval would be 0 to 2. Third interval being 2 to infinity. I need to plug in a point into the second derivative for each one of these to determine the sign of the second derivative. I'll use the factored version of it, 12x times x minus 2. I'll pick one in the first interval. How about negative 10? Second interval, how about 1? Third interval, how about 10? If I plugged in negative 10, I'd have a negative times a negative, which is positive. If I plugged in 1, I'd have a positive times a negative, which is negative. And if I plugged in 10, I'd have a positive times a positive, which is positive. I go back to my sign, or to my number line. I have positive, negative, positive. Again, it was 0 at 0 and 2. And remember, when a second derivative is positive, my function's concave up. When a second derivative is negative, it's concave down. Again, positive means concave up. If you notice at both of these points, it does change concavity at 0 and 2. So both 0 and 2 have to be inflection points. I do need to plug those numbers in. F of 0 I did on a previous page for finding the y-intercept. That's 5. I already knew that. So I know the point 0, 5 is an inflection point. I'll write that down now. 0, 5 is an inflection point. But now I need to plug in the number 2. If I plug in f of 2 into my original function, that'd be 2 to the fourth minus 4 times 2 cubed plus 5. I'm getting negative 11. So that means the point 2, negative 11 is also an inflection point. 2, negative 11 is also an inflection point. I look for when it was concave up. It was concave up whenever the second derivative was positive, which was on 2 intervals, those 2 intervals being negative infinity to 0 and 2 to infinity. I look for when it was concave down. It's concave down when the second derivative was negative, which was on the interval 0 to 2. I have now analyzed the second derivative in entirety. So what do? Take the information from parts A, B, and C and put them all onto one giant number line. All right, so let's start with the information from A. A says the domain's negative infinity to infinity. Great, we can't graph that. That doesn't help us. But B says that it's the y-intercept is 0, 5. So we're going to have to draw a y-intercept here. Again, I'm totally making up the y value on this. I'll say it's something like there, right there, 0, 5. That's all the information from the first one. Let's go to the second one. From the first derivative, it looks like we broke it up when x equaled 0 and x equaled 3. So I'm just going to go ahead and make some tick marks here. 1, 2, 3. I'll do some negative ones as well, just for fun. So here's the point when x equals 3. Okay. All right. So what did we get? Let me go ahead and drop that line when x equals 3 also. We knew that the derivative, I'm going to look at the sign of the derivative on these, and the second derivative. So the sign of the derivative was negative, and it was 0, then it was negative, and it was 0, then it was positive. Okay? What else did I get on there? I got that there's a minimum at the point 3, negative 22. So go ahead and plot that now somewhere. I'm just going to make it up. How about right about here? And I'll label that 0.3, negative 22. So that's going to be my y value of negative 22. Again, my y scale is pretty much crap right now. I don't really care about the y scale. What I care about is the shape and the behavior of the graph in each one of these intervals. Okay, so now that we've analyzed the first derivative, let's take all the information from the second derivative. The second derivative says break it up at 0 and break it up at 2. That's what we did on the number line, so we'll do that again here. Let's take that information. It went from positive, and again, this is the second derivative, went from positive to negative in the middle to positive along the whole end. So let's see what happens. The first interval that we have to consider, and those were inflection points between. Remember, at 0, 5, I had an inflection point. I've already plotted the 0.05, but another point that we could plot is the 2, negative 11. So I'll put that right about here. Here's the 0.2, negative 11, trying to keep it semi to scale. That's going to be an inflection point as well. Okay, so let's put this together and determine the shape of the graph. My second derivative is positive, so I have to be a smiley face. The first derivative is negative, so I have to be decreasing. So it looks like the left half of the smiley face is what I have to be for the first section here. So I'm going to go to the 0.05, and I'm going to make it look like the left half of a smiley face to the 0.05. Let's go to that middle part from 0 to 2. From 0 to 2, my second derivative is negative, so I know I'm concave down. My first derivative is negative, so I know that I'm decreasing. The right half of a frown is decreasing, so the shape of my graph has to be a right half of the frown. So I'm going to go from the 0.05 to the 0.211 using that right half of a frown shape. Notice I would have an x-intercept in there. I do cross the x-axis. I don't know the exact value, so I'm not going to label it. All I would do on this problem is, if this were on an actual test where I was allowed technology, I would use the technology to find that x-intercept. Okay, let's look at this next one. Don't forget this interval. It is from the 0.2 to 3 is what we need to look at. From 2 to 3, my second derivative is positive. My first derivative is still negative, so it seems like I change to the left half of a smiley face in this point right here. So from the 0.2, negative 11 to the 0.3, negative 22, I'm going to do the left half of a smiley face. It did change concavity. That is an inflection point. That's good. And then let's go on to the last interval. It's second derivative positive means smiley face. First derivative positive means increasing. So that means I need to be the right half of a smiley face on the end of that. So if I'm the right half of a smiley face, again, I'd be creating another x-intercept. I don't care what it is. What I really care about here is the general shape and behavior of the graph. So it seems to me like this is the shape and behavior in a nice rough sketch of the original function, x to the fourth minus 4x cubed plus 5. Again, this is using absolutely no technology. So all we did was analyze the original function for domain, x-intercepts, y-intercepts. The first derivative for increasing, decreasing, maxes, and mins. The second derivative for concave up, concave down, and inflection points, and put it all together, and we're able to get this nice rough graph here. At this point in time, I'd go to something like desmos.com or use any graphing utility you have to verify the graph of the function. Make sure the behavior is correct. Again, our y scale is going to be really off here, but I want you to make sure that the shape of the function is correct in each one of those intervals.